Welcome back to the second session, and you know how they sometimes say, well, the next speaker needs no introduction. I think in this case that's quite true. I haven't actually checked the stats, but Sachin may well be our most frequent presenter, and I'm quite fine with that because his presentations are always fun and incredibly interesting and also very topical and cutting edge. And today's promises to be no exception, where he talks about a topic close to my heart, as you saw in the early presentation about the upcoming Bayesian course, where he talks about probabilistic programming and deep Bayesian networks. So he's taking his current great passion of deep learning, deep neural networks, and he's combining it with his extensive experience, in fact his PhD topic, of Bayesian statistics. So he's going to be showing us how to use the PyMC3 package, which is the Hamiltonian Monte Carlo Bayesian stats package in Python. He's making a point of saying he's not using Stan. For those of you who don't know much about Sachin, the 3 or 4 of you, he did his PhD in Bayesian machine learning, but he's since gone on to become a master of deep neural nets, deep learning, if you will, and his deepschool.io has attracted millions of views and made him an international superstar on the deep learning instructional scene. He's currently working in sports betting, which is about as cutting edge as you can get in a machine learning job. And over to Sachin.
So today I'm going to be talking about Deep Bayesian Nets mainly. So just a quick background. My PhD was on Bayesian machine learning, but after I left my PhD and my postdoc for that matter, I've been pretty much heavily involved in deep learning and deep learning alone. So I actually said goodbye to Bayesian world. In fact, it's kind of ironic that I'm even talking about Bayesian because I don't like Bayesian. So mainly they're slow. Unlike deep learning, you have to think about the features, so you have to do feature learning. Have to think about the data generation process, which is okay. But and the last thing, it turned out, like for me, what I found out was that it's not that I hate the Bayesian process, I hate Bayesians. So actually, let me take the poll. Over here, who's used deep learning in this room? Who's actually played around with it? Okay, who's played around with Bayesian methods? Okay, that's a good start. Who would call yourself a Bayesian?
Now.
This is awkward. Okay, so Bayesians are people who well, my definition, use Bayesian methods only and assume that Bayesian is the only way of dealing with the problem, right? So, and I completely disagree with that. So you do whatever you need to deal with the problem, and then Bayesian might be a method to deal with it. So I started coming back into probabilistic programming as soon as I started looking at Stan. So Stan was the very first probabilistic programming language that I used. It was amazing. Now that I'm using Python, PyMC3 is the best alternative. Actually, there's some functionality that goes beyond Stan, at least from my definition. There's TensorFlow probability, I haven't used it so much, and then there's Pyro. The common thing between the last three is that they lie on top of a deep learning platform, right? So PyMC3 uses Diana, TensorFlow obviously, and then Pyro is on PyTorch, right? Anyway, so the main thing that these guys came and did is that really they democratized Bayesian learning. So what I mean by that is that you don't necessarily have to have a maths background or stats background to get into Bayesian learning. So for me, that's the best part about this thing. And second thing, and even without knowing the maths, you can do approximate Bayesian learning, which makes things a whole lot faster. Okay, so now unfortunately there will be some maths, okay, so I apologize. Yes, some people clapping. So, hey. So I think one message that I want to get through though is that yes, there is some maths that I show, but hopefully you understand that the maths can be disregarded as well. Okay. So the first thing that I'm going to be going through is a simple example where a sample from a normal distribution now, and I want to find out what the mean is. Okay. Actually, before that, just quickly the Bayes rule. That's the Bayes rule that you're most familiar with, right? So the example, again, coming back to that, what I'm going through is the mean is going to be 4 and the standard deviation is 1. Okay, so what I want to find is what is the posterior, what is the mean given the data. Okay, so you can go through the maths and check it if you want to later, but I've done it for you for now. So yeah, anyway, this, what have I done? Okay, so this is basically how, given 100 observations, how I would go and update the posterior mean. Okay, so just a quick video of this video, but that's how the mean converges, right? So so the more and more data that I get, it's starting to converge onto the mean of 4. Okay, and the second thing you should really notice is that the variance is starting to decrease. Okay, so that was a mathematical way of doing this. I manually found the equations to get the mean and the variance. Let's try and do this the PyMC3 way. So the PyMC3 way, you need to write down the model. Okay, so the model in this case is that you have the mean of 0. So I assume that the prior, okay, so I know nothing about the mean, so I'm going to assume that the mean is somewhere between 0, not between, like the middle is 0, but it has a huge variance. Okay, so basically I don't know anything about it. But the observations, they have a mean of mu and standard deviation of 1. Okay, so I'm telling you that the standard deviation is 1. We'll play around that a little bit later as well. Yeah. Oh, by the way, do people use Jupyter notebooks here?
Yeah.
Yeah. All right. Turns out that you can write LaTeX equations. Well, you can do this. Right. So you write down your LaTeX equation and press tab. You get your Greek letter. So if that's going to be one takeaway, that's probably going to be it. Right, so once you write down your mathematical model, you write it down like this. Okay, so these equations correspond to these 2 lines. Right, so the best part about this is that I can just go PM.sample. Right, and it does the maths for you, it samples it for you. Right, so underneath it's using a method called NUTS, which is some HMC method, but anyway, again, the point is you don't need to know about that. Right, so you can use it completely out of the box. So yeah, so after I do the sampling, so after I run through this 100 observations, the reason that I have 4 lines is because I have to parallelize it before, so I'm not sure why it's not combining all 4 plots. But yeah, so that's what it ends up looking like. Okay, so you can see that it's somewhat centered around 4 and standard deviation of 0.2 or so. Right. So in the previous model, I said, I told you that the standard deviation is 1. And another thing you can do is say, okay, I don't really know what the standard deviation is, so I can put a prior on that as well. So in this case, I said, okay, again, I don't know too much about what's going to happen with the standard deviation, so I put a wide prior on it. Okay, so in this case, I say the mean is probably 5, which it's not, right? So it's much smaller than that. But yeah, so again, I go ahead and check, just write those 3 lines over here. Okay, so this is what probabilistic programming is. You write down your model and then you sample. Okay, so yeah, so in this case, you have the mean as well as the standard deviation as your posterior. Okay, everyone good with that? Okay, so let's go on to today's talk, which is on the deep learning aspect of this. Before I move on to the deep learning aspect, so Bayesian inference, it's not about the Bayesian rule as such, right? So the Bayesian rule over here was what you probably learned in high school with this thing over here, with this equation. But the Bayesian rule is slightly more in the sense that we integrate out any kind of parameter. So if you're doing linear regression, the weights, we would integrate all possible values of the weights. Okay. So let me come back to what I mean by that. So what you usually do, effectively what you usually do is you find the most likely value of your weights and you plug that into your equation. If you do linear regression, for example, say you only have one x and you find that the coefficient is 2, that 2 over there is the most likely value, right? So with Bayesian, with the posterior thing that we just did before, you have a distribution of that. But the Bayesian inference aspect is that you integrate out all possible values, which is equivalent to saying you plug in all of that and then average it across. Okay, approximately equal to. Anyway, so that's the Bayesian inference aspect of it. So, okay, so in this example, what I'm going to be doing is I'm going to be looking at the MNIST dataset. So everyone's aware of what the MNIST dataset is. So it's a handwritten dataset, digits go 0 to 9. Okay, so it's 28 by 28 pixels. And what I do is I flatten that. Okay, so a big mix, 780 something pixels. And I'm just going to be doing a multinomial regression. Okay, so this is very much linear. Okay, so the only difference to normal regression is that you get the probabilities out of each thing being a certain number. Okay. So how do I code this up in PyMC3? So what you do in this case is the only thing that has prior is the weights. Okay, so nothing else. So the weight was the only thing that I had a distribution over. Right, so I have pm.normal, so normal distribution, and the rest is just what you would do with normal or deep learning or normal linear regression. So you just multiply, you matrix multiply your input with the weights, and then you take the softmax or across all of those. Okay. So you need to know what the categorical means. So this is the categorical distribution. Okay, so basically it's choosing, it's 1 or 0. Okay, so it's choosing the probability that it will be that particular digit. Okay, so in this case it goes from 0 to 9. Right. Right. So what's the so the machine learning aspect comes from the fact that this is faster than just sampling. Okay, so before I did pm.sample, which was proper, what do you call it? MCMC sampling, whereas this one, what it's doing is variational based. Okay, so it's an approximation, and yeah, so that's why I wrote the prox. And what it's doing is it's minimizing a loss function. All right. So instead of searching through your entire space, which is what proper Bayesian methods is supposed to do, this is minimizing loss function, which I've written down the maths for. If you want to go and check it, you can do it later. But yeah, so that's what's happening. Okay, so you can see that it's not quite converged yet, and there's still a lot of variance of what's going on. So one of the best things about PyMC3, and which is getting into the deep learning space, is you can do batch updates. Right. So right now, as I put in the 50,000 data points straight into this thing, and because of that, it's struggling to find some sort of local minimum fast enough. Right. So this was, okay, so I didn't let it run for too long. So it's only 16 seconds, but it had not run for longer. Where am I? Okay, let me come back to the batch thing later. But the best thing about doing this is you get a distribution. Okay, so yeah, so that is this is from my test set. Okay, so I look at it too. But when you're with the normal machine learning methods, you would just get one single probability of saying this is number 2, right? Whereas over here, what's happening is that you're actually getting a distribution across 2. Okay, so there is a chance of it being 0. It's a continuous distribution between 0 and 1. Okay, so that's the best. That's the reason that you do Bayesian inference, right? So when you want to have uncertainty, right, rather than a single value saying this is what you should be, what your prediction should be. Okay. So that's really the strong point over here. So you can see that it's starting to say it might be a 3 as well, right? Or it might be some other number as well. So yeah. So once I do the mini batch part of it, right? So I take 256 values at a time only. Then it starts to converge a lot more. So you can start to see it's starting to level off now. But yeah, so the accuracy is 91%, right? So whereas before the accuracy was 82%. And by the way, when I say accuracy, the way that I got the accuracy was to say, look at the average. So I sample 500 values from all those probabilities. I look at the average and take the maximum probability to be the true value, the true predicted value. Okay. So that's how I got the 82% over here. Once I do the media batch updates, I jump to 91. So hopefully you're starting to see how this can feed into deep learning as well. Right, so I got my media batch updates, which is a big part of deep learning. So I am using Piano underneath. So yeah, again, so looking at the number 9, so this time it's quite confident that it is 9. It might be a 7 as well, but one thing you might notice is compared to the histograms before, so you can see that there's like residual stuff in everything, whereas over here it's quite confidently saying most of them are 0, right, except 7 or 9. It turns out that the 9 is a bit more confident when you look at the numbers over here. All right, so deep Bayesian networks. If you heard me talk about deep learning in general, deep learning is nothing more than stacked regressions. Okay, so there really is nothing more to it. Sure, there are tricks that they use to make things faster, make things a bit more accurate, but at the end of the day, that's really a big part of it. Right, so this time, I initialized 3 set of weights to have normal distributions, but the rest of it is just going, okay, I matrix multiply the input with the weights, and then take the ReLU function, again, and then, yeah, so the last 3 lines are exactly the same as the previous model. Okay. But yeah, so this time, once I do this, I did look at this, did train this for a bit longer, but my accuracy goes up to 94%. All right. Yeah, and just lastly, one other thing that I did was I tried rotating these images. Right, so the rotating images, because it wasn't part of the data set that I'd seen before. So in this case, it was a 9, and then I started rotating 45 degrees at a time. Because it hasn't seen this before, I want to see what the probabilities are going to be. Right, so you'll start to see that, yeah, so it's starting to say 7, right? But the thing is that the other numbers as well, the numbers are creeping up. Okay, so it's non-zero probabilities. So once I go across, yeah, so there's a whole bunch of other things as well that's coming up and saying, this might be true, right? So
definitely a 7. Definitely.
It is 7, yes. Yeah. So once I get to there, so it's starting to look like 6, sure, but so when it does turn all the way around, like I'm pretty sure the 6 there is, like it is saying it's a 6 if you take the average, but there's high variance over there as well, right? And the reason might be the case that it's curving backwards, the 6, right? So people normally write the curve the other way, right? Normally, but yeah. So yeah, again, the point being, there's a lot of uncertainty in this. So that's most of my talk. So just quickly, I know like a lot of this would have gone over your heads for most people, right? And if you did keep up, great, thank you. But what I really want you to take away from this is, once you get home, just look up Stan, look up PyMC3, depending on what your choice of programming language is. Because if you ever want to deal with uncertainty, Bayesian methods are like one direct way of going through it. There's a book called Bayesian Methods for Hackers, so it's a GitHub book, and that's a really good place to start. So again, it's Bayesian Methods for Hackers, not for statisticians. Okay, so the main thing with PyMC3 is that it's allowing programmers to get into Bayesian methods, and not just statisticians. PyMC3 examples are a good point. And just quickly, I'll just show you one other thing that I worked on. So I was trying to model some stocks just to see how they vary. But like what I was really interested was in the covariance, right? So this time the model structure was sure it was a bit more complicated, But the best thing about this is, again, I could code it through with a few lines, and I can start looking at the covariance of each of those stocks. So in this case, Apple, Microsoft, Google. It doesn't have the names on here, but the ones with the positive correlations are the ones with those stocks, right? So why am I showing you this? Because the reason I'm showing you this is to show that probabilistic programming is easy, right? It really isn't complicated. If you had to write down the maths behind it and do the posterior, yeah, sure, it will be extremely difficult, right? So yeah, so PyMC3 or Stan or any of the other languages really simplify these things for you. Yeah, so that's it. Any questions?
I will make the first question if you don't mind.
Yeah, his hand up, but
No, he doesn't have a microphone. He
Kind of
can.
make a question. Disadvantage of being one of the organizers. So is this part of your deep school set of examples?
So this thing I actually did today, so it's not up there yet, but
That probably would be there.
yeah, I will be putting up the GitHub link.
Thank you. Now the gentleman.
Oh, right, yeah.
Yeah, it's me, the question hog. I'm just interested, what is it about this programming language that has lent itself so well to your methods that others haven't? Like in R or maybe MATLAB or like other Commonwealth. Yeah.
So this is, so everything that I'm doing is in Python, right? So probabilistic programming, it's nothing to do with the programming language. It's just the fact that I can write the model like this in a coding fashion rather than a mathematical fashion. So it doesn't refer to the actual programming language. PyMC3 just happens to be one of the tools that I use among many.
Thanks for your talk. I previously tried to use PyMC3 for a project, and I had to give it up because the sampling speed was just taking too long for what I was trying to do. First of all, how long was the actual sampling part of running your algorithm, and do you have any tips to make it go faster?
Yeah, that's a good question. So if you use the normal PM.sample, that's probably one of the things that would be taking you too long, right? So that's the actual MCMC method of doing things. But if you use approximation method instead, which the only thing that you need to do is you change it to PM.fit, and it goes a whole lot faster. But anyway, I can talk to you offline.
Like what kind of magnitude faster are we talking about?
At least 100 to, well, compared to the MCMC method, 100 times there. If you use mini batch sampling, that's another 10 times over that. So there's always a few more tricks you can use.
Are you able to use this in a production or commercial environment?
You can, because it's Python, right? So
No, I don't mean the restrictions. I mean in terms of speed to performance. Because if you are in a commercial environment and you have a web page and your expectation is 300 millisecond response time, are you able to achieve something like that?
So you always train your model offline, right? So as far as inference goes, yeah, sure, you can certainly speed this thing up. But I'll talk to you afterwards about that.
Question here.
Yeah.
Yeah, hi. Just out of curiosity, a non-technical question here. What's a real-world application of deep learning that no one is looking at the moment, in your opinion?
I really don't know the answer to that. Because as long as there's data that you can gather, you can always apply deep learning or Bayesian methods too.
I suppose a better question is, what's something, say in the last week or so, that you said, I wish someone looked at, but no one's actually looked at?
It's a pretty open question, right? So, yeah, look, like nothing on the top of my head. So.
Fair enough.
Yeah.
Thanks for the talk. I was just wondering, when you're using the variational loss, do you still get posterior distributions over all of the parameters of the deep network?
You get approximate distributions. So, so what does tend to happen is that it gets stuck in modes so when you're going through the loss, it does get stuck in the modes. And again, with the approximate thing, you generally say it's fixed to be just a Gaussian, right? So if your posterior is multimodal to begin with, then that's an issue. But so there is some work on getting to fit multimodal distributions as well, which PyMC3 codes up for you, and you don't have to worry about, right? So you just literally in the pm.fit, you just go method is svgd instead, and it does that bit for you, right? So you don't actually need to read the paper.
You mentioned in these Bayesian methods the powers in quantifying the uncertainty.
Yep.
But for a lot of these, it looks like we're just kind of looking at the histogram. And what makes it so much more powerful when, for example, in the last example, you can kind of just, to quantify the uncertainty, you could go 1 minus the probability that's estimated. That's, in some sense, kind of its confidence. You just go into a little bit more about kind of the power of that.
Of the uncertainty over one number, right? Yeah, okay, so I think, let me just go to one of the simple examples. Yeah, like this one, right? So, if I did in normal machine learning fashion, it would just go, the probability is going to be 0, 0, 0. Okay, it'll give 0.2 to 0.27 and 0.7 to 9, something like that, right? But the problem of that, like I see what you're asking, that it's already giving you a probability. Okay, but it's not giving you distribution, right? So it's giving you one number saying, I am very certain that this is with, I'm very certain that this is with 0.7 probability that it is 9. Okay, but the thing is, like with this thing, you're actually seeing that there is a continuous variation. So there is a chance that it's not 9 at all, right? So yeah, so okay, let me give you a bit of context, right? So I work in sports betting. So if you're going to look at a particular horse winning, your models might give you, say, this horse is going to win with 100% probability. Okay, depending on, it might be a bug in the model, but yeah, it'll do that. Whereas a Bayesian model will say the probability of this horse winning is between 0.9 and 1, right? So there's a bit of a variation. So when you try and bet, you don't want to, if it's saying 100%, you know you're going to put the money there, right? But yeah, so if you want to be a bit more careful, that's what you do. You look at the distribution.
Yeah, hi Sachin, thanks for the interesting talk. You mentioned the IMC3 is backed by Theano and there are a few other packages. I read also that Theano's end of life, 2017, no more updates. Is that going to limit IMC3 and maybe?
No, because they're going to be moving to TensorFlow next year. So yeah, so they are maintaining Theano for now. But I think next year it'll be back by TensorFlow, so it's not,
Thanks.
So that was the last question. Well, you can ask more questions during what networking time is left, but can you all please join me in thanking Sachin? As is traditional now, we open the floor to anybody who has announcements, particularly about jobs that may be going. So, do we have any hands? Once in a while we get recruiters. Recruiters are welcome to come up and say something about positions that are going. I guess I should say that Alpha Zeta is certainly looking for data scientists and data engineers to join our happy crew of independent data scientists, independent data engineers, people who don't have a day job but have what we call a portfolio career. So if there's any interest in that, please come and talk to me in the 5 or so minutes before I leave tonight. Otherwise, thank you all very much for coming. Oh, you've got an announcement.
One very quick one, yeah.
Yeah.
All right, I'll just yell. So I'm working with a couple of mates to put together a bit of mankind versus machine challenge. You've all been hearing about AutoML and all the cool stuff that's been going on this year. You're all really good data scientists in this room, I'm sure. But aren't you curious to see how good these models are these days? Aren't you curious to see if you can actually still beat them? So anyway, next Friday, just pulling people together, walking through a bit of it's backed by GA and a few other people, so there's going to be some nice swag. And it's just a nice opportunity to play with some of these really cool AutoML frameworks. That's it from me.
Thank you. Any others? Yes.
Hi everyone, I work at Bright, B-R-I-G-H-T-E with an E at the end. We're fintech with a mission to help Australians save the world by installing solar panels and batteries. We'll help finance that. We're looking for data scientists. If you're interested, please come see me. Thank you.
Going once.
We don't use IMC3 at Bright.
Going once, going twice. Sold. Go home, people. Thank you.
Thanks everyone for coming. Just a quick one. With all the visitor passes that you have, kindly remember to put it at the door. There's like a nice little return place. And also, there's a few of us here at CBA from the data science team, such as myself and Pash. And if you're interested to have a quick chat about the current opportunities, talent acquisition is at the back with Ankit, who's raising his hand. Yep, so yeah, thanks for coming.
Hi, I'm Jim Pearce. I'm the Director of Health Policy Analysis, which is a consulting firm in healthcare. It was with great pleasure that we've been able to sponsor the videoing of the latest meetup of Data Science Sydney.